This morning, we'd like to begin by hearing from Professor Helvi Witek from the University of Illinois on the Canuda thorns. Helvi?
Yeah. Hello, good morning, everyone, or good afternoon. I would like to tell you a bit about science in the strong field regime of gravity. So let me start by sharing my screen so that you can actually see my slides. And yeah, I'll do it this way and then have the full screen mode here. And yesterday, Steve asked us what brought us actually into contributing to the Einstein toolkit. And in my case, it was really more the science than the computer science, if I'm completely honest, because I was interested in probing the strong field of regime of gravity with black holes, which also means that we may want to go beyond general relativity for our field equations, or that we want to tackle new fields to gravity. And to make this science possible, I have developed a numerical relativity library, which eventually I called Canuda, and actually was not just myself, was in collaboration with Miguel Ziliao at the time, and more recently with my PhD students, Matthew Alley and Giuseppe Ficara, that makes those new studies possible. And then I said, well, if I have this code, I want to make it public. Why not contribute to the Einstein toolkit? Because that's a great platform to make code public. It's reviewed, so we have a assurance of quality. We have the documentation, and it's a really open and inclusive community. So that's what brought me into the Einstein toolkit here. So what I would like to do today is walk you through two science cases, and then give you a very brief introduction of how Canuda is structured. So I'm not going to go into very much detail. And if you're interested, I'm happy to discuss after the talk, or if you have time, Steve, later on. So if anyone has any questions, I'm happy to talk about it. I will also apologize in advance if there are any clunks. I just moved essentially 2 days ago and just got internet yesterday. So I hope everything goes fine. If not, please bear with me. Okay, so let's get started. As I said, I want to talk to you about two science cases. The first one is about black holes coupled to light fields, where these light fields can be dark matter or dark matter candidates, and more generally, that will allow us to study particle physics beyond the standard model using astrophysical black holes. So that's actually a really cool and exciting research program, and I will tell you a little bit about the motivation of how we can do that. And the second science case is, well, labeled searching for quantum gravity, but it's really trying to understand nonlinear effects in gravity if you modify Einstein's equations. And then the last part here is a brief introduction to the library Canuda. Okay, good. So one of the big questions that we have in modern physics is, of course, what is dark matter? And I illustratively show you here footprints of someone walking through the snow. What it is, we don't know. So we see the footprints, we know that someone or something was there, but it's hard to tell what that something or someone was, whether it was just one person, whether it was several people, whether it was an animal, we have no idea. The gravitational footprints for more than 80% of all matter are, for example, seen in galaxy rotation curves, where you measure the velocity profile in galaxies. You would expect a profile like shown here in green, where the velocity of material decreases as you go to the outer edges of a galaxy if you were to include only the matter that you can see. So let me call that ordinary matter. What is measured, however, is something like this yellow curve here, where the velocity stays almost constant. And if we backtrace that, we find that there has to be an additional component of matter that we don't know what it is, and that's why we call it dark matter. We can also see these footprints of dark matter if we look at gravitational lenses, where light is bent through to a strong gravitational field. So you can see here these light rings, and sometimes the universe may even smile at you for trying to understand its secrets. Okay, so what is dark matter? Well, here is a comic version of dark matter candidates. Can go from, well, weakly interacting particles, neutrinos. They also put some more exotic fun stuff like space cows. But to be more serious, what we are interested in is on this low energy end here, which is called axions. These are very light particles that you get if you compactify string theory. So in lay person's terms, so from string theory, you quite naturally get an entire landscape of very, very light fields at and below the energy regime of microelectron volts. And interestingly, we can use black holes to look for exactly these very, very light particles, these ultralight particles. And what we are using for that is called black hole superradiance. If you don't know what superradiance is, well, imagine an analogy where you're trying to go off a muddy road, and as you put more and more energy into going off, instead of leaving your muddy road, you will just transform this energy into energy of your mud that's then spilling out. For black holes, the analogy would be, or the process is the following. You have a rotating black hole, as we have in astrophysics. You have a scalar field or a vector field, a wave packet going onto your black hole. And if it has a very low frequency, then instead of just falling into the black hole, that field is actually amplified. So instead of falling in, it gets out with more energy and more angular momentum than it had initially, and that's called superradiance for black holes. And of course, at the expense, so in this process, the black hole itself loses mass and angular momentum. Now, if you imagine that this field has a mass term, so as an ultralight field, then having this mass essentially gives you a potential wall, so that this field is then trapped near your black hole. And because the superradiance scattering continues until the condition is no longer met, we can actually build up a bosonic condensate, which is what I'm illustrating here. Yeah, so there is this phenomenon called superradiance and superradiant instability that I just described to you, and that allows you to form these kind of bosonic condensates around black holes. Now, people have studied that extensively in the literature, including perturbative calculations and fully nonlinear calculations that I will mention in a moment. In a certain regime, so if you say, oh, my coupling between the black hole mass m and my mass energy of the field, which we call mu, is much smaller than 1, we can actually solve this problem analytically, and we find that the energy spectrum of my scalar field resembles that of a hydrogen atom. So we find that this actually has these discrete energy states here. And what you then can imagine is that we have transitions between these different energy states that give rise to extra radiation. Turns out that this is gravitational radiation that we can try to look for later. And because of this structure, people have termed this system a gravitational atom. Unlike the hydrogen atom, however, this system is not stable. So in the hydrogen atom, our frequency is completely real, so this is all there is. For these ultralight fields, for this gravitational atom, the frequency is complex, and the imaginary part of the frequency tells you if this field is still growing. So if this frequency is positive, the field is growing. If it's negative, the field will be decaying. And it also tells you the time scales of this instability, of this separating instability. And it was found that the instability is shortest for highly rotating black holes and can be as short as 50 seconds times the mass of your black hole measured in solar masses, or for vector fields, this time scale would be 5 milliseconds times the mass of your black hole measured in solar masses. And that's the case if your black hole itself is originally highly rotating, and if this coupling, gravitational coupling, m times mu, is of the order of 1/2. Or in other words, if you write this out and reinstate the natural constants, you find that this is actually a gravitational radius compared to the Compton wavelengths of your field. So if that is of comparable size, then you have a very strong separating instability. Now let's do one more calculation and actually insert what these constants are, rewrite the equations a little bit. Then we find that this coupling would be 10 to the 10 times the mass of your black hole measured in solar masses times the mass of your, or mass energy of your field measured in electron volts, has to be of the order 1/2 or half. Now let's do one back of the envelope calculation, and let's think a little bit. So if we take the black holes that we have in astrophysics, so take the mass of the black hole here to be between, say, 5 solar masses and 10 to the 10 solar masses, then we can actually estimate a range for these ultralight fields that we would be sensitive to. And that's what I've done here on the next slide, where I tell you what the black hole mass is, what the mass energy, and I apologize for not being consistent with my notation here. So this should be mu measured in electron volts, so the mass energy of our ultralight field. And the top line here are actually the gravitational wave detectors that we already have, or that we are planning to have in the future, which would probe these the certain types of black hole population. So let's start at the right hand with the black holes that we have already detected with ground-based detectors like LIGO or Virgo. So here we're talking about a few solar masses, 3 or 5 solar masses, up to order 100. And using this back of the envelope estimate that I showed you on the last slide, we would be sensitive to ultralight fields in the mass range 10 to the 11, 10 to the minus 11, 10 to the minus 12 electron volts. If we go towards the supermassive black holes here with 1 million solar masses that we expect to detect with LISA in the future, LISA is a space-based gravitational wave detector that is currently planned by NASA and ESA that will look for gravitational waves in the millihertz regime, so coming from these million solar mass black holes, and that those would be sensitive to fields that have a mass of 10 to the minus 17 electron volts. If we are looking at 1 billion or 10 billion solar mass black holes, we would use pulsar timing arrays, and those would be sensitive to fields with a mass 10 to the minus 21 electron volts. Now that may sound very exotic, but these kind of fields actually appear as axions or axion-like particles in string theory. So if you're talking about fields that have a mass of roughly 10 to the minus 10, 10 to the minus 8 electron volts, we're talking about the QCD axion that was introduced back in the 70s by Petcher and Quinn to solve the strong CP problem. Then if you're talking about these very light fields, these have been realized as candidates for fuzzy dark matter. And in the string axiverse scenario that Asimina Afinataki proposed a bit more than 10 years ago, one expects an entire range of these light particles. People also are thinking about extensions of general relativity that may give you an effective mass term. So this is a long list, and I could probably go on and on and on. But the key message here is that we can use black holes in astrophysics to probe for dark matter and more generally for beyond standard model particles in a way that's not accessible to traditional particle colliders, and that's not accessible to direct detection experiments that are looking for dark matter candidates. So this is actually a really, really cool physics that we can do here with black holes and make a connection to particle physics. And the observable signatures, that would be the last slide for this topic, could be the following, that we say, well, remember, if we look at superradiance, that effect will reduce the mass and the spin of black holes. So there should be gaps or holes in the plane if we were to plot black hole spin versus black hole mass. And in fact, people have used that to constrain some of these ultralight particles. People have started to look at the effect of the superradiant instability on the shadow of black holes. So most remarkably, Carlos Heredero and his collaborators have a series of papers on that. More recently, one of my former students and I have looked at the evolution of the black hole shadow as induced by superradiant evolution. And we also have gravitational wave emission, for example, through these level transitions in this, what we call the gravitational atom. And we find from numerical simulations that I've done a few years ago, that the frequency of the gravitational wave quadrupole would be roughly 20 kilohertz divided by the mass of the black hole. Or in other words, for black holes that are in the LIGO range, this frequency would actually be of a few hundred hertz, so would be exactly in the LIGO range. And for supermassive black holes, that frequency would be in the millihertz regime, so could be detected or searched for by LISA. And here I'm showing you one example, and so those of you who have attended a few times have already seen this plot, where I'm showing you the gravitational waveform mode as a function of time. And that's output from a numerical simulation that Miguel Zillao and I have done, where we studied mass effector fields around rotating black holes. And in the right mass range, we see that this gravitational wave signal here is almost monochromatic and can be very long-lived if you look here at the blue line. And as I said, that's one of the outputs that we had gotten with Canuda very early on in this system. Okay, so that's the science case for black holes as cosmic particle detectors. Do you have any questions here? Let me just pause for a second. And since I don't see anyone, please speak up if you do have a question. No? Okay, so then let's look at the second science case. And again, a very ambitious question. Is there a question?
Helvi, I have a question.
Okay, yeah.
If these light particles were detected, if you were to see something, would you know if it was an axion or something else, or just would you know that it's something?
So in this case, we would know it is something, as in with black holes, we are sensitive to the gravitational interaction. Right? We are not, so in this particular case here, we are looking for the gravitational interaction, so we can see that there is something that is interacting, but we are not looking at the coupling to standard model particles.
So you wouldn't know exactly what it was you were seeing.
So we wouldn't know exactly what it is, but I think it's also a strength because we are not relying on any precise model of coupling to the standard model, right? So we are much broader and have the ability to search for any kind of extra matter that is interacting gravitationally, as long as it is in this mass range.
Okay.
Yeah.
Thanks.
Okay. Any other question? No. Okay. So then let's continue with the second science case. Again, asking a very ambitious question. What is the theory of everything? And I think that's what people have asked for quite a long time. More precisely, it's maybe a question of what is quantum gravity? How can we combine gravity and gravitation and quantum physics that are both strong pillars in modern physics? We know that general relativity, as beautiful as it is not a good candidate for quantum gravity because it's not renormalizable. It has all kinds of singularities, such as a physical singularity inside a black hole. So the question is that actually physical, or is that just an indication that general relativity starts breaking down at very high curvatures? And of course, we do not know the answer yet, but we do have a few candidates for quantum gravity. If you take those and take the low energy limit, it turns out that we can actually study extensions of general relativity. So think about it in terms of, because we're not really knowing what it is, think about it in terms of a Taylor expansion, where we have GR at the leading order term, and then we start adding theoretically well-motivated modifications. What I want to do today is not going through the entire zoo of modifications that there are, but want to focus on one, and that's called Einstein-Dilaton-Gauss-Bonnet gravity. And in this case, what you get is Einstein's equations that are coupled to a scalar field, which is called a dilaton. So think about it as a scalar field if you don't know what it is. And then you get additional terms indicated here by a curly G and a curly R that are essentially just Riemann curvature squared type terms. Yeah, so if you're not familiar with it, think about it as your model being Einstein's or GR at leading order, and then you have a curvature squared type correction. And that correction is coupled to a scalar field. So your field equations would be Einstein's equations coupled to the canonical scalar field energy momentum tensor, and then has a correction here that involves the scalar field and the metric, and you get also an equation of motion for your scalar field that is sourced by the Gauss-Bonnet invariant, so by the space-time curvature itself. So this is really just a Riemann squared type term, and if you have no ordinary matter, this is actually the Kretschmann scalar. Yeah, and as I mentioned one slide ago, that kind of theory actually appears if you take different candidates for quantum gravity and just take the low energy limit and reduce down to 4 dimensions. Now, what's interesting here is that your black holes are no longer the black holes of general relativity, but you find that they have additional scalar here. And you can actually see that from this equation here, as we have the scalar field, so equation box phi, sourced by the Kretschmann scalar, sourced by spacetime curvature itself. So even if you start with a 0 scalar field initially, what you will see is that the scalar field will grow as sourced by your curvature in the background. And that's actually quite interesting because now you can think about taking 2 of these black holes that have scalar here. And that's what I'm going to show you on the next slide, where I show you an animation from about 2 years ago, where we looked at a binary black hole, which is in the background, which is sourcing a scalar field. And what you will see in the animation is the equatorial plane of the system and the scalar evolution of the scalar field as driven by our black hole binary. Okay, so let me just put this on, not show this again. Okay, so here let me just make that a bit bigger. So here we see the scalar field being strongly excited by the black hole. So these coincide with the black hole collision, black hole positions, sorry, that are orbiting around each other in the background. These blobs have different size because our black holes have a mass ratio of 1 to 2. And you see that because each of those black holes has a scalar field with a monopole configuration, we start exciting scalar dipole radiation. So you should be able to see that being excited here as the black holes approach each other, this radiation becomes stronger and stronger. So scalar dipole radiation. Now the black holes have merged. We see a burst of scalar radiation going out, and the final scalar field resembles that, or is essentially the scalar here that you have around a single rotating black hole. Okay, and this is a theoretical study to see the effects of the scalar radiation. And now so we did the following estimate, and we said, well, look, if we have a black hole binary that's in spiraling in GR, transmits a certain energy, now our black hole binaries have this additional scalar here. So, and as we've seen in the simulation, we are also emitting scalar radiation, which means that the system, the binary, emits more energy in this modified gravity theory, which means that it should inspiral faster, and ultimately the gravitational wave signal should have a phase shift if you compare it to GR. Now, can we use that information to tell anything about the theory or about the coupling in the theory? And in fact, we can. So by not observing such a phase shift in the measured gravitational waves, we can actually try to forecast bounds on this kind of coupling. And that's what I will show you in this rather busy plot here. So this is on the y-axis, we have the coupling to our Gauss-Bonnet term measured as a length scale. And we are looking at a range of black holes from about 5 solar masses to about 100 solar masses. So really in the range for ground-based detectors. And the different lines are the following. So all the black lines correspond to the sensitivity of LIGO. All the orange or yellow lines correspond to the anticipated sensitivity for third generation ground-based detectors that will improve by about an order of magnitude in sensitivity, 2 orders of magnitude in sensitivity. And the different line styles correspond to different mass ratios. So we have the solid lines are for equal mass black hole binaries. The dashed lines have a mass ratio of 1 to 2, and these dashed dotted lines have a mass ratio of 1 to 4. Now, what we can see is just by the back of the envelope estimation that I just described, we can already place bounds on this kind of coupling. So everything that's above those respective lines would be excluded. So if you have an unequal mass black hole binary, we can place stronger bounds on our coupling. And as we increase sensitivity, we can also place stronger bounds. So we will be able to further constrain this kind of model in the future. And for comparison, I'm putting here this green dotted line, and that's essentially a bound coming from the fact that black holes should still have regular horizons, and that actually gives a limit on what this kind of coupling can be, and then we can compare to the black holes that we have already observed. So here we see that by looking at this late in-spiral and merger, we can place bounds on this coupling that are stronger than previous bounds, although of the same order of magnitude. What I have not plotted here, but what's more interesting, is that we are giving bounds that are about an order of magnitude better than those that you get if you just look at the early in-spiral phase, as for example, people like Kentyagi or Nico Yunus have done in the past. Okay, so that's the part on testing gravity in the nonlinear regime. Do you have any questions before I continue?
I don't, but we have you scheduled to finish up in about a minute.
Oh, okay. Okay, can I?
You raised his hand.
Okay, so now I do the thing that I usually don't like to do. Can you give me 5? Because what I wanted to do now rather quickly is actually tell you a bit about the code that we've used to do these kind of simulations.
We do have two questions. Peter Diener.
Yeah, so I was just wondering if the effect of the hairy black hole binaries is just that they merge faster. Couldn't that just be interpreted as a standard GR system with lower mass?
So that's actually a very good point. So it's not so much the mass, but the spin, which I have completely ignored here. But that's absolutely right. So there's some degeneracy between black hole parameters in GR and the spin. However, last year there was a paper by Ramir Nair and collaborators who have done a proper Bayesian parameter estimation and found similar bounds on this coupling. But yeah, you're absolutely right. So one has to understand very carefully what is what would be the non-GR effect, and how can we distinguish that from a GR system. Yeah, that's a very, very good point. Thanks.
Atul?
Yeah, hi Helvi, thanks for the talk. I was going to ask if a similar study has been done for an F of R gravity, which is kind of similar to the theory that you've introduced, but I think it's kind of simpler because it's just R squared terms are included alongside the basic Riemann-Kurowitsch tensor R. So has it been done?
So the first question would be, do you still have hairy black holes in that case, or do you get scalarized neutron stars? I'm not aware that this has been done in the late inspiral and merger, but I would expect starting in the early inspiral, so probably a post-Newtonian type calculation.
Okay, okay, but a study has not been done, I'm guessing, is your answer too?
Not that I'm aware of.
Not that you.
There is. Okay. So let me trace back a little bit. There is a very nice paper by Bishop Mongwane in South Africa, who has derived the field equations in BSSN form that could be implemented numerically. But
okay,
I'm not aware that that has actually been done. So I remember talking to him where he had that planned, but I don't think he has done that.
Okay, thank you very much.
Yeah.
Okay, so try and finish up in about 5 minutes.
Okay, I will do that. So it's really a very, very quick overview about the code library that we've used for this. So thank you for your patience. So the code library itself is called Canuda. And this is one of those half-finished slides. So Canuda is named after a library in Barcelona that features in The Shadow of the Wind by Carlos Ruiz Zafón. And both Miguel Dollao and myself are a big fan of that series of books. So that's why we decided to name our code library after that historic library in Barcelona. Also was at the time when we both were living in that city. This library, as I said, was developed together with Miguel Dollao. So what we are doing is developing different set of arrangements, or developing one together if you have a common interest, and then reviewing each other. And more recently, my PhD students, Matthew Alley and Giuseppe Ficara, who both are in London at the moment, have started contributing to the library and developing new pieces of the code. Canuda is available in a public Git repository. Here I can send you the slides later, Steve, if you want to make this on, put this online, and also copy that in the chat after the talk. And we created a DOI following the Einstein Toolkit example with the Nodo, where we have this database reference. So if you use Canuda, please do cite at least this database. And we also give some information on the wiki and the repository about the papers that should be cited if you use our library. That is to say, this library, once we have cross-checked the code, is public. Now, part of Canuda is in the Einstein Toolkit. So, for example, we have one piece of the code that is called lean public, that is based on a code that Ulrich Sperhake developed originally, and I apologize for not putting the name here as I should have. And that's actually an arrangement of Thorns that evolves Einstein's equations. So that's essentially an alternative to McLachlan. And I think Zach used that as example to develop Baikal. So when I reviewed his code, I actually could compare very easily to our own here. So that's a gravity evolution SORN, and also gives wave extraction and a wave extraction SORN that's complementary to the Wilf scalar in the Einstein toolkit. We also have the Proca SORN in the Einstein toolkit. So Proca is essentially a massive vector field and goes back to the first part of the talk. So it gives us the evolution of massive vector fields. It reduces to Maxwell's equations if you take the mass to 0. So you can also evolve Einstein-Maxwell systems with the Proca arrangement, and I will tell you a bit more about this collection of SORNs in a minute. Now, what's not yet in the Einstein toolkit or outside is an extension of the lean public SORN. So one of my students has implemented or has connected our original implementation to Llama, so gives you now a multi-patch infrastructure, which is well tested. And if there's interest, we could include that in the Einstein toolkit. So just throwing that out here. Then we also have an arrangement of SORNs that evolves a massive scalar field. Again, we have already included multi-patch infrastructure here and are finishing up the tests. And this is a collection of SORNs that gives you a definition of grid functions, different types of initial data, and the scalar field evolution itself. And then we have an arrangement of SORNs that's called Canuda EDGB in the decoupling limit. So that's the collection of SORNs that allows you to simulate black hole binaries in Gauss-bounded gravity. And again, we have included a multi-patch infrastructure here. And again, it's as I said, a collection of SORNs. We have the base SORNs where we define grid functions, initial data, and evolution. Now, let me talk a bit more about how we can connect, for example, our Proca arrangement together with gravity. And that will be the last slide, Steve, so almost there. So what we want to do is have some space-time where we have gravity. We want to simulate vector fields, maybe even a massive vector field, interacting with our space-time. So we what do we need for that? So we need a collection of SORNs that helps us with a DR spacetime. And I'm focusing here only on the physics SORNs. So I'm not talking about anything that gives us a grid setup. And we will have our collection of massive vector field SORNs, and we will have some kind of coupling between the two. Now, as you've probably heard in the beginning of the week, we have one SORN that defines our grid functions, and they are usually labeled have a name and then underscore base. So ADM base, for example, defines our metric grid functions. TMU base would define the grid functions for the components of the energy momentum tensor. And then Proca base defines our vector potential and electric field. Then we have, and these talk to each other. Then we have initial data. If you want to simulate a black hole binary, this is 2 punctures. If you want to have that black hole binary carry a Proca field configuration, we have a code called 2 punctures underscore care Proca, and it's actually not for binary, it's for a single black hole. So that was a mislabeling that we should correct. And we have also other types of initial data here. Then in red, we are describing our evolution SORN. So we have McLachlan, we have lean public. Now I should add Baikal as well. So we can couple any of these to our Proca evolution, and they talk to each other through this TMU base up here. And then to understand and extract physics, we again can use SORNs already available in the Einstein toolkit, like the parent horizon finder, wave extraction SORN, or our own wave extraction SORN. And then we complementary have the wave extraction for the Proca field. So that's the general structure. And if you wanted to couple any of the other arrangements that I mentioned, They will have a very similar collection of thorns and will couple in a very similar way to gravity. Okay, and with that, let me just finish. So I hope I could interest you in this program that we can use strong field gravity to probe and understand open questions in fundamental physics. I gave you two science cases. The first one was looking at the interaction between black holes and ultralight fields, which would help us to search for or constrain dark matter candidates and more generally beyond standard model particles. The second science case was looking at black cobinaries and scalar Gauss-bounded gravity, so looking at modified gravity. And I gave you a very, very, very brief overview on the code library that we used for that, which is called Canuda. Part of it is in the Einstein toolkit. If there's any interest, we are very happy to make any of the other arrangements available to the Einstein toolkit. And with that, I thank you and take more questions.
We've got a question about where the documentation is located. We can probably handle that offline.
Yeah.
I don't see any hands raised. Okay, so